And we'll start our new material. So last week we left off talking about sampling distributions. And sampling distributions for a population proportion population parameter, I should say, involved a couple of steps. One, pick a sample size. That sample size is going to be n. Take all possible samples of that size from the population. Measure the statistic from each sample. So if we're measuring the proportion, you'd measure the proportion. If we're measuring the mean, you'd find the mean of each sample. And those statistics make up the sampling distribution. So what does all that mean? Well, I'm going to jump over to Excel here. If I can get Excel to come up. Oh, maybe it doesn't want to come up for me. There we go. Be just a second. My computer's running a little slow tonight with some new updates. Hopefully we'll have Excel up and running here in just a moment. And what we're going to do is we're going to make up a population. Then we're going to pick a sample size, and we're going to take all the possible samples of that size from our population. Here we go. Okay, so we've got it going now. So here's what we'll do. We're going to pick our population here. My population is just going to be 4 numbers: 4, 7, 10, and 14. There's our population. Population mean. Well, let's do the mean of those 4 numbers. 8.75. Population standard deviation. Now, again, we got to use the dot P because this is considered a full population. There's a standard deviation. And now we're going to pick a size. And for our purposes, it's going to be n equals 2. So our sample size is of 2. So now we're going to pick all possible samples of size 2, n equals 2. So we can have 4 and 7, 4 and 10, 4 and 14, 7 and 4, 7 and 10. Oops, I don't want to, 7 and 10. I don't want to repeat the backwards one. 7 and 14, 10 and 14. Oops. So those are all the possible samples. Order not included. We could, 4 and 7 and 7 and 4 are going to be considered the same sample. So those are all the possible samples that we can take from this set of 4, where we can get sample size of 2. Well, for each of those samples, let's find the sample mean. Well, for 4 and 7, that would be 5.5. We go all the way down here, get all those sample means. These means of each of those samples, this is the sampling distribution. Notice, the actual values range from 4 to 14. These sample means are a little bit smaller range. They're because there are several numbers averaged together or combined together into a mean. They're not going to have as big of a range. There's going to be less variation. Remember, we talked about this before. If there's a small value in the sample, chances are there's a large value in there too, and they cancel each other out to get a mean somewhere in the middle. But now we have the mean of these means. I'm going to go over a notch. And that is going to be the average. There. And notice that is exactly the same as our population mean. So the mean of those sample means is always going to be the same as the population mean. Now, a little bit trickier is the standard deviation of those means. Sometimes called the standard error of the means. Now, the rule we have is that it's going to equal the population standard deviation divided by the square root of the sample size. However, that applies only if we are looking at an infinite population. That is, the population is really large compared to the size of the sample. Here it's not. The sample is half the population. So it's not quite going to work out that way. But let's just do the adjusted, what we would call this, the expected standard error here. And that's just going to be the population standard deviation, or here, the 3.6996, divided by the square root of the sample size, which is 2. So we would expect this standard deviation of these sample means to be about 2.616 if we had an infinitely large population. Now, this is also a population standard deviation. But notice it's not the same. It's not 2.616. It's smaller than that because, again, the population was small compared to the sample, or the sample was large compared to the population. In order to avoid this, the sample size has to be less than 5% of the population. Some books say 10%, 5% to be safe. Otherwise, you have to do something called a finite correction factor. Look, finite population correction factor. And what that is it's simply the square root of capital N minus little n over capital N minus 1. And of course, you got to put in the square root there. My draw tools are not working tonight. Huh. Okay, well, we'll do this. None of those tools are working tonight. So anyway, I'll leave it at that. So to do that calculation, we're going to take this value here, the expected, times that correction factor, the square root of 4 minus 2 divided by 4 minus 1. And that corrects for the fact that this is a very small population compared to our sample size. And you can see there we do get the exact same value. So let's back out of there. So this is what we had discussed last week. That correction factor, by the way, is the square root of capital N, which is the population size, minus little n, which is the sample size, over capital N minus 1. This is what we talked about last week when we were estimating a population mean. Well, this week, we're going to do a sampling distribution for a population proportion. And it's really quite similar. So once again, we select a sample size. That sample size is n. Now, in this case, n is generally quite a bit larger when we're dealing with a proportion than it is when we're dealing with a mean. So now we select all possible samples of size n from the population. Calculate each sample proportion. Those proportions now are the sampling distribution of the population proportion. So just like all those sample means were the sampling distribution of the population mean, here the sample proportions are the sampling distribution of the population proportion. And the characteristics will be similar. The mean of the sample proportions will equal the population mean, or the population proportion. So if I take those samples and I find all their means, or find all their proportions, the mean of those proportions should be exactly equal to the population proportion. The standard deviation of the sample proportions, once again, sometimes referred to as the standard error of the proportions, a little bit more complex here. It's going to equal sorry about this, technical difficulties everywhere tonight. My computer seems to be having some memory issues. Sorry about that. Let me close down some of my side programs going here. So anyway, as I'm waiting for the computer to catch up on things here, the standard deviation of the sample proportions is also going to be related to the standard deviation, similar to like what we did with the binomial distribution. We had the standard deviation of that. Now it comes off of that same concept. Here we go. Okay, I think I'm back live. Now let me back out of here and share again to make sure everything's working fine. Okay, so maybe it isn't. There we go. Okay, so I think their system is caught back up. Sorry about that. So let's get back to the screen here. So this standard deviation of the sample proportions is the square root of P, which is my population proportion, or the estimate of the population proportion, times 1 minus P over that sample size of n, with some restrictions. or we had to have a sample size of at least 30. For the population proportion, we have to have certain requirements met as well. One is that n times p has to be greater than or equal to 10. This is the expected number of successes. And n times 1 minus p has to also be greater than or equal to 10. That would be the expected number of failures. So we have to have a large enough sample that we can honestly expect at least 10 successes and at least 10 failures. Not as big of a deal if we have a proportion close to the mid-range, close to that 0.5 or 50%. More of a concern when you have a really small or really large proportion. If your proportion's, only like 7 or 8%, you need to make sure you have a sample of at least 80 or 90 so that you can honestly expect to have, well, not even that, at least 150. So you can honestly expect to have at least 10 successes in that sample. Second, the sample size n has to be less than 10% of the population. That's why we had that finite population correction factor in our example, because the sample size was larger than 10%. And of course, the sample is a random sample from the population of interest. So not too strict of requirements, not too hard to come up with. See if I can make my mouse work here again. Okay, there's back. So what we want to do is we want to take a look here at an example of this. I can't really simulate this one in Excel because I could just take a long time to do the simulation like we did with the sample mean. But let's do this. Let's say that it is known that 78% of students pass statistics on the first attempt. A random sample of 200 statistics students is chosen. What is the probability that at least 80% will pass on the first try? Now, unlike with our sampling distribution for the means, where we could compare it to the probability of a single value, we can't do that here. The probability of a single student passing on the first try is just the 78% or 0.78. But we can look at the probability of a group of 200 students. So this is going to end up being normal CDF of 160, I should say, to 200 with a mean of 78% is going to be, we'll just put it as 200 times 0.78. Calculator will accept it that way. And then times our square root of 0.8 times 1 minus 0.8 divided by our sample size of 200. So let's put that in a calculator and see what comes out for us. So we're going to go second, distribution, normal CDF. So we are going from 80%. Well, that's 200 times 0.8. I typed in as 160, which is what the value actually is, to our upper limit, which will be the full 200. Our mean is 0.78 times the 200. And our standard deviation will be the square root of 0.8 times 1 minus 0.8 divided by the sample of 200. Close that parentheses. Paste that in and let's see what we come up with. Ends up with 0. It's almost impossible to have more than 80%. Let's run that through again, make sure. Let's do this. Go from 200. I'm going to type in 60 here just to make sure it's calculating that right. And I'm going to type this in as 156 just to see what happens there. Okay. So I entered something wrong here. Let me show you what it is. I needed to enter not the raw numbers, but the actual percent. So I'll put in the 0.8 here. Up to, this will be 1 or positive infinity. Either way, but 1 is all I really need. They're up to all of them. Put in 0.78 here. And then we'll do the paste. And now we'll still get 0. Oops, what happened there? Something did not overwrite. There we go. Sorry, there it overwrote. So we get the 0.2397. So that is what we were looking for there. So what I needed to enter was the actual percentages or the proportions. So I want to know the probability of more than 80%. That's the 0.8. Let me go back to that whole command there. Up to 1, which is everything. Now, I'm going to put in positive infinity here just to show you that we should get pretty much the same answer with a mean of 0.78 because it's known to be the proportion. And then that standard error calculation. And you see, if I put in positive infinity instead of 1, I get the exact same answer because this is a proportion. Got somebody in the chat room here. Well, yeah, typically there's something been entered if you get a 0. Not always, but usually rather than getting a 0, you would get scientific notation like, 3.2 E negative 12 or something like that. You would get a really, really small number, but you wouldn't necessarily get a 0 unless there was something wrong in it. That is correct. So let's take a look at find the probability that less than 70% will pass on the first try. So this one's going to be very similar. I should change this command up here. I'll get rid of that.
Professor Hall?
Yes.
Would you be able, oh, you're doing it already. I was going to ask if you would be able to, never mind. Thank you.
You bet. So this command up here was 0.8 to positive infinity or 1 because it's a proportion. 0.78 and then the square root of that part does not change. So this one being less than 70% will be a similar command. Less than, of course, goes from negative infinity. But since it's a proportion, we could just go from 0 to 0.7. That's the 70%. With the mean of 0.78. And of course, the square root of 0.8 times 1 minus 0.8 divided by 200. So again, let's enter this in and see what comes up. So second distribution, normal CDF. Now we're going from either 0, or we could have gone from negative infinity up to 0.7 with a mean of 0.78 and our standard error again of 0.8 times 1 minus 0.8 divided by 200 of 0.0023. So very low probability there. But this was, I believe, 0.2397, if I remember correctly. And my calculator just shut down on me. That's not good. So the next question I want to ask is, how does this change if the sample size is changed to 200 or just 100 students instead of 200? So what would that make a difference? Well, let's redo both of these probabilities for a sample size of 100. I'm going to do the bottom one down here first. So I'm going to go to the calculator. Hopefully I got the calculator up and running. Looks like I don't. Let's get it going over here. So give me just a second to get my calculator rebooted. Apparently my computer is getting to the point where it's time for a memory clean. Okay, hopefully I can get in there now. So this is the less than 70%, but we're still dealing with, we're going to deal with a sample size of 100 instead of 200. So this is from 0 to 0.7, still with the mean of 0.78, but we're going to change this to a sample size of 100 instead of 200. Now we see that's a significantly larger. It's 0.0023, I believe now. It's 0.0228. So much larger. The smaller sample, it's much more likely that that smaller sample is going to deviate further away from what the population value really is. So let's do the same thing here for greater than 80%. So we're going from 0.8 to 1, from 80% to 100%. Oops, just 1, not 100. And everything else is going to stay the same. And this should also be a larger probability. And there it is, 0.3085 is what we're ending up with there. So the smaller the sample size, the more likely it is that we get a value further away from the mean or the true population proportion. The example I want to show where we use this is assuming there is no preference. What that means is the population proportion is 0.5. In other words, 50-50, half go one way, half go the other way. There is no preference between options A and B. Would it be unusual for a survey of 80 people to show more than 55% prefer option A? First of all, what is unusual? Statistical definition of unusual is a statistically significant number that is chosen, typically 0.05. If it's not given, we use 0.05. It can be 0.1 or 0.01, either one, depending on the importance of the test. It's something we'll discuss a little bit more when we talk about hypothesis testing. So anyway, let's go ahead and calculate this probability. So it's a normal CDF, 0.55 to 1, if the true population proportion is really just 0.5. And the square root of 0.5 times 1 minus 0.5 divided by our sample size of 80. And let's see what we get here. second distribution, normal CDF from 0.55 to 1 with a true population proportion of 0.5. And let's see here, the square root of 0.5 times parentheses 1 minus 0.5 divided by the sample size of 80. We get 0.1855. So that probability 0.1855 is not less than 0.05. So it is not unusual. That's because the sample size of 80 was pretty small. What if the sample size is 400? This might make a big difference. So we're going to go to the calculator here, second distribution, normal CDF. All that changes here is this standard error. And instead of 80, we're going to divide by a sample size of 400. We get 0.0228. So that is unusual. So I'll put the command here. All that changes is the 400 instead of 80. Okay, so we'll move on from that. The next thing we want to discuss is using these normal probabilities as an approximation to the binomial distribution. Once upon a time, before these calculators came around and they could do, the cumulative binomial calculation, which saves us a ton of time if we have more than a handful of items for our sample size of n. We would have to, at one point, we'd have to do a separate calculation. If we had less than 17, we'd have to do a separate calculation for 0 and for 1 and for 2 and all the way up to 17, and we'd have to add them together. So it was useful to be able to approximate. So we're going to approximate binomial probabilities with the normal distribution. So let's do n equals, little n equals 20. And p equals 0.3. Find the probability that x is less than or equal to 10. So for the binomial probability, this would be a binomial CDF, 20, 0.3, and 10. CDF would be cumulative, so that would do the less than or equal to. Second distribution. Get down to our binomial probabilities here. Want the binomial CDF. We're at 20 trials, probability of 0.3. And we're going up to 10 is our X value. And we get a 0.9829. So again, with a modern calculator, real easy to do that calculation. But again, back in the day, you'd either have to look up in the tables, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or you'd have to calculate all 11 of those probabilities yourself and add them together. So let's use the normal approximation. The normal approximation requires us to find, of course, the mean is n times p. So that's going to be 20 times 0.3, so it's going to be 6. standard deviation, which will be the square root of n times 1 minus, or sorry, not n, p times 1 minus p times n. So here that's going to be the square root of, I'm going to expand it a little bit, 20 times p of 0.3 times 1 minus 0.3, which comes up to be, we'll punch this in off screen, square root of 20 times 0.3 times 1 minus 0.3, giving us 2.049. Now we could actually just put that whole expression into the calculator, but we don't need to. And what we'll do is the probability here now of being less than or equal to 10 is actually the probability of being less than 10.5. Why do we do 10.5? Well, because remember the binomial distribution is discrete. It can only take on the values 8, 9, 10, 11. It can't take on any of the values in between. Well, the normal distribution is continuous. It can take on the values 9, 10, and 11, but every value in between. So in order to make sure that we don't just cut it off too soon, we have to go halfway to the next number. So between 10 and 11, there are an infinite number of possibilities in the normal distribution. Half of them are going to go with the 10, half of them go with the 11. So that's why we went to 10.5 here. So we'll go to the calculator. What was that? 2.049. Second distribution, normal CDF. And we're going from 0 to 10 with a mean of 6, standard deviation of 2.049. And we get 0.9728. So it's a little ways off, but it's not terribly far off. 0.1 is the difference. Part of that might be the round off in the standard deviation. Let's do this. Instead of putting in the 2.049, let's put in the whole calculation here. The square root of 20 times 0.3 times 1 minus 0.3. See if that makes much difference. No, not a lot. So we end up with, this said, very close, 0.9728 instead of 0.9828. But it's a good approximation if we're trying to save the effort of having to go through all of those calculations. The last thing I want to talk about is assessing normality. How do you tell if a set of data is normal? Well, first of all, box plot. Your box plot, if your data is approximately normal, you should have your box in the middle. The mean should be pretty much close to the middle of the box. The whiskers should be about the same length as each other, but also longer than half the box. This box plot would be something I would say is pretty close to normally distributed. A dot plot. Same type of thing. You have your number line. And you have your dots. And it's a little slow to draw out, so I'm not going to draw a lot of them. But you can see there, your dot plot forms approximately the bell curve. If I were to sketch a line through the top of those dots, I get pretty much a bell curve. And we can have a histogram. The histogram will be the same type of situation. We're seeing bars. They get progressively larger as we get to the center of the data. And make a relatively symmetrical distribution. I didn't do the greatest job of sketching that out, but you guys get the picture. The biggest thing is there can't be any outliers. Like on the dot plot, if there were a dot way out here, well, that means most likely not normal. Or on the box plot, if there was an extra bar out here, or on the box plot, the histogram, if there was an extra bar out here somewhere, definitely not normal. On the box plot, if there was an outlier at one end, probably not normal again. So we could use these types of things to figure out if a data set is normal. Now, there's also norm quantile plots that your book goes through. And in the norm quantile plot, I would prefer to do this in Excel if I can get it to work again. Let me try it. Hopefully it doesn't lock everything up on us again. But what a norm quantile plot does is it puts the data forces it into a normal distribution. And then we check to see if that's an appropriate representation. So let's do this. Let me quit share out of here. So here's my data set. I'm going to do 7, 11, 12, 14, 15, 15, 18, and 22. So I'm going to take these values, and actually, let me do this. And I'm going to just put them in order. They're already in order, but I'm going to put them in a column. So 7, 11, 12, 14, 15, 15, 18, and 22. There's my data sets. I'm going to assign each of them an I value. So I'm going to number them 1, 2, 3, 4, all the way up to this one only goes up to 8. So then I need to put in a column here. I'm going to move these down. And this is going to be my AI number. My AI number is found by taking 2 times this number up here. This is the first one. So let me do this. So equals 2 times this number minus 1. And then it's going to be divided by 2n. Well, here n is 6 or 8. So 2 times 8, so it'll be 16. And I get 0.0625. And I'm going to do that for every number in here. So what you see is I get evenly spaced numbers from 0 up to 1. This is the normal equivalent of the probability of being less than this number if this were normally distributed. I'm forcing a normal distribution onto this data. Now I want to do an inverse normal for the AI. Values. So here we're going to do an inverse normal, or norm inverse for this value. Oops. So I got probability of this, mean of 0, standard deviation of 1. And there we go. We'll do that for each of those values all the way up. And notice we start with a negative value, then on the other end we have a positive value. It's the same. That should be exactly how it works out. These are z-scores, and these are claiming to be the z-scores for these values over here. So now what I want to do is I want to take these values here, I'm going to copy and paste them, put them here. And then I'm going to take these values, I'm going to copy and paste them. Now I have to be careful that I paste special here. Back. So I paste just the values, not the formulas. And then I'm just going to graph these. So I'm going to do a scatter plot. With just those points. So across the bottom here was my data points, 7, 11, all the way up to 22. Up the side here, those z-scores. Now, the closer this comes to being a perfect line, the closer this data is to being perfectly normally distributed. Well, this is not bad. It is fairly close to a line. So I would say this data set is pretty close to being normally distributed. I mean, if it were perfectly on the line, we know it's exactly normally distributed. If they're scattered all over the place and obviously not linear at all, or there's a curve or whatever, then we know, oh, again, it's not linear. But here the data points are reasonably close to that line, so we could say that they are linear. Well, that is all we have for this week. It's a little bit of a light week, partly because, of course, we had the midterm exam last week. We want to say a little bit about that. Make sure a midterm exam should be finished now. Technical difficulties having flustered tonight. If you have not finished, you need to send me a message right away. Because we have to take care of it right away, only if there's some extreme circumstances. If that's not the case, you might be stuck without the midterm exam if you don't have it done at this point. So please get in touch with me right away if you haven't taken the midterm so that we can get that figured out. I will be posting midterm grades over the next few days. I do go through all of those exams and go through the grading. So it'll take me a little bit of time to go through and make sure that I agree with the way Alex graded your exams. Usually gives back people a few points at least on the exam. So with that, I will end my lecture. Does anybody have any questions?
I do. It's concerning the midterm exam.
Yes.
So I had a huge issue with my exam. I ended up having 3 different proctors while I was taking my exam, and